On July 1st, 2025, the Survey Telescope Network's Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile recorded an object that would soon be designated 3I/Atlas, the third confirmed interstellar comet to enter our solar system after 1I/Oumuamua and 2I/Borisov. Interstellar objects differ from ordinary solar system comets because their trajectories are not gravitationally bound to the Sun. Their orbital eccentricities exceed 1, allowing them to pass through the system only once before returning to interstellar space. The unusually high velocity and the inbound direction of 3I/Atlas made clear that it originated beyond our solar system. Astronomers quickly dedicated significant telescope time to tracking this rare visitor, monitoring its brightness, observing the development of its coma, and capturing early spectra. The object moved rapidly, with estimates placing its heliocentric speed at around 209,000 kilometers per hour, fast enough that any disruption in observation risked losing crucial information. This became a real problem in late September, when a remarkable and unintended alignment of maintenance schedules caused a 36-hour gap in Western optical and infrared observational coverage. At the Hubble Space Telescope, a gyroscope calibration cycle temporarily halted imaging. JWST shifted instruments from NIRCam to the mid-infrared instrument, a transfer requiring thermally induced downtime of more than a day. The European Southern Observatory's Very Large Telescope entered a scheduled mirror cleaning cycle using carbon dioxide, snow, and nitrogen jets. And Gemini North and South rotated into time blocks reserved for pre-approved exoplanet and planetary science programs. Individually, these pauses were routine, but taken together, they created an unexpected global blind spot just as the comet passed into a region of sky near the sun's glare, where even short observational delays degrade scientific precision. For active comets, such gaps carry consequences. Outgassing, dust release, and structural changes in the coma and tail are often most intense near the sun, and missing those moments means losing the ability to reconstruct the timing and magnitude of peak activity. In stark contrast to the paused Western observatories, several Chinese facilities remained fully operational. High-altitude telescopes in Tibet, Qinghai, and Yunnan continued uninterrupted work because their maintenance schedules and night sky windows did not overlap with Western downtime. These Chinese observatories became the only continuous data sources during the blackout, effectively serving as the world's eyes on the interstellar object. This episode underscored how global astronomical coverage is limited by the weakest synchronized link. Even with numerous advanced telescopes, a simultaneous pause in one hemisphere can open a significant observational void. In the case of 3I/Atlas, that brief window translated into lost measurements of outgassing rates, dust-to-gas ratios, and morphological changes in the coma, information essential to understanding the comet's composition and formation history. As the gap unfolded, astronomers turned their attention to the developing coma, tail, and gas release behaviors. The coma, a diffuse halo of gas and dust that appears when solar heating causes ices to sublimate directly into vapor, expands dramatically as a comet approaches the sun. Dust and gas, pushed by solar radiation and the solar wind, form the tail, which can stretch for vast distances across space. Beginning in mid-July, instruments including Hubble and JWST provided key insights. Hubble's high-resolution imaging helped constrain the nucleus's size, though estimates varied, possibly as large as 5.6 kilometers or as small as 300 meters, because the bright coma complicates the separation of nucleus and surrounding dust. More revealing were the compositional measurements from JWST and the Sphere-X mission, which detected a coma dominated by carbon dioxide outgassing, with water vapor appearing only in minor amounts. This was particularly noteworthy because water typically dominates sublimation in solar system comets as they warm. The high CO2 to H2O ratio suggested that 3I/Atlas likely formed in a colder region of its parent system or underwent a very different thermal history before being ejected into interstellar space. During the Western blackout, the uninterrupted Chinese observations became essential for preserving the continuity of the comet's observational record. They captured brightness evolution, positional changes, coma expansion, and tail growth, an echo signal of how the comet responded to increasing solar radiation. Without those data, the peak activity portion of the comet's light curve, crucial for modeling jets and rotational behavior, might have been permanently lost. The Chinese observatories that filled the gap leveraged both geographic advantage and resilient technical infrastructure. Facilities such as the Ali Observatory in Tibet, the Delinga Station in Qinghai, and the Yunnan Astronomical Observatory operated at high elevations with thin air and low humidity, conditions that significantly improve signal-to-noise ratios. Their telescopes, typically 1 to 2.5 meters in diameter, funneled incoming light to cooled CCD or CMOS detectors, with liquid nitrogen cooling systems reducing thermal noise. Each exposure was calibrated using dark, bias, and flat field frames to correct pixel non-uniformity and electronic noise. Because the comet moved rapidly across the sky, shifting about 35 arc-seconds during the blackout period, exposures had to be kept short, usually between 30 and 120 seconds, to prevent image trailing. Every frame included GPS-synchronized timestamps accurate to the millisecond, ensuring that astrometric measurements could be precisely aligned when comparing data from different sites. Images were stored in FITS format, preserving critical metadata such as filter type, exposure length, telescope location, and environmental conditions. Automated pipelines at each facility performed background subtraction, starfield alignment, and centroid calculations to derive brightness and positional data. Harsh mountain conditions posed challenges. Temperatures could drop below -20 degrees Celsius, requiring temperature-controlled enclosures and redundant power sources ranging from diesel generators to photovoltaic arrays. Data traveled via fiber optic links to low-altitude centers for archiving and integration with global catalogs, such as those maintained by the Minor Planet Center. During the blackout, the Ali and Qinghai stations captured continuous imaging in B, V, and our photometric filters, enabling calculation of color indices that revealed unusually large carbon-rich dust grains in the coma. By the time Western instruments resumed operation, the Chinese servers had already accumulated hundreds of gigabytes of images and spectra. These files formed the only uninterrupted record of the comet's activity over that crucial 36-hour interval, functioning as a scientific heartbeat monitor for an object that otherwise would have gone untracked. The blackout itself was not the result of crisis, but bureaucracy. Astronomy relies on complex scheduling systems that allocate telescope time months in advance, primarily through proposal queues designed to balance scientific priorities and instrument maintenance. A convergence of such scheduled operations produced the September observational void. At the same time, survey systems that might have offered fallback coverage, like Pan-STARRS in Hawaii or the Atlas Network, were occupied with other mandates, including tracking near-Earth objects. Radar observatories, such as NASA's Goldstone Solar System radar, could not compensate because 3I/Atlas was far beyond their detection range. Goldstone cannot effectively track small icy bodies beyond roughly 0.1 astronomical units. To the public, such gaps often go unnoticed because telescope systems do not stream continuous video but rely on discrete exposures taken at specific intervals. When those exposures stop, the scientific record becomes punctured. For this comet, the missing data represented a break in the light curve, impairing the ability to determine rotation period, jet behavior, or transient activity. This highlighted a structural vulnerability in global astronomy. The overwhelming concentration of large telescopes between 20 degrees north and 30 degrees south latitude means downtime in one hemisphere disproportionately affects worldwide coverage. Although smaller observatories elsewhere exist, few have the sensitivity or spectroscopic power of major Western facilities. Thus, when the West went dark, responsibility for continuous tracking shifted entirely eastward. The uninterrupted Chinese observations not only bridged the temporal gap, but prevented large positional errors. By the time Western instruments came back online, 3I/Atlas had moved more than 1.2 million kilometers. Without the intervening Chinese astrometric measurements, predicted coordinates would have been off by tens of arcseconds, large enough to cause instruments to point at empty sky. Once collected, the Chinese observations entered a detailed and highly structured data pipeline. Mountain Station FITS files